Danny. Yes, hello everyone. My name is Roma. I just finished my PhD at Brown with Ellie Pavlik, and I'm now a research scientist at Google DeepMind. Today I'm going to be talking about how we can use insights from game theory and multi-agent decision-making to improve language models, but then also the ways in which we can use language to help improve these multi-agent reinforcement learning settings. I actually didn't realize how similar Jacob's talk that was just before mine was going to be to mine, so I'm going to skip through a little bit of the motivation of why language models are great, how good they are, and come to this point where you can imagine this classic multi-agent setting where you have two cars in this environment, and what you would want in order for this game, this cooperative game, to function well is for the cars to be able to have awareness of each other and maybe even learn how to communicate with each other in order to exist in this environment without crashing and causing both of them to die instantly. There's been a lot of work, all of the citations before, that show that in this setting, instead of just training in a standard multi-agent reinforcement learning way, where you just have an agent learn a policy, which is really just a set of actions that allows it to move forward in the environment, instead of just learning an action policy, if you can also learn a communication policy, where both agents now also learn how to send sets of messages to each other in order to signal to the other agent what part of the environment they're in. This communication policy with the action policy actually does allow the agents to perform a lot better, so they can now navigate around each other better and have less crashes in the environment, which is great to see. However, it's also worth noting that this isn't only the case for these cooperative games. Even if you have the two-player zero-sum game where the agents are maybe not cooperating with each other, but actually have to oppose each other in a zero-sum environment, even over here, having this communication policy has been shown to be very helpful to agents. However, what a lot of these works usually do is they learn this sort of discrete symbolic communication channel that's not actually interpretable to humans. So it's just a series of bits as part of this communication channel where some sort of semantics is assigned to each of these messages. But as a human, if I look at this set of messages, it's not actually interpretable to me, but the agents can just use that to assign some sort of meaning to parts of the environment to each other. So agents converge on this language that's very different from human language and not really interpretable to humans. Importantly also, apart from just generalizing to humans or having a human understand this language, it's also not the case that any agent that's trained outside of this environment can even understand this language. So there's lots of reasons why this is suboptimal. And also, given that this symbolic language is so different from human natural language, these protocols are somewhat harder to learn. They don't follow a lot of the properties of natural language, like compositionality, or having the words follow some sort of distribution. This language is less efficient and is therefore not ideal for lots of reasons. So to surpass this, what we want to do is to now try to train agents to communicate in natural language, mostly because we can. We know how to get LLMs to do this sort of thing now. And what this means is, what we want in this sort of two-player game is for both agents to maybe start from a vocabulary, which is natural language, that now has some sort of prior semantics that's attributed to the symbols or the words in natural language, as opposed to a discrete set of messages that all of the previous games work, and then allow this reinforcement learning multi-agent self-play to shift the semantics of this general natural language that was learned from the internet to this task specifically that the agents are playing in. So what this means is you could start with a pre-trained language model that's been trained on all of the internet. It has this giant vocabulary where semantics are attributed to the words that is understandable to humans. But what we want to do now is to now fine-tune a language model with another language model or another agent in an environment to now shift the semantics to be more task-specific. So for example, maybe the word red has some sort of meaning in the world, but now in an environment where you have something that's pink and something that's blue, you know what the word red refers to in this environment that's slightly more task-specific and different from the prior semantics of that word. Reasons that we want to do this is because in these pre-trained language models, this general purpose training has resulted in this model of language that's a good generative model and has lots of knowledge and facts about the world. But again, it's not task specific, and it's not specific to this one environment in which we might want, for lots of efficiency reasons, the semantics to shift slightly to allow the agents to communicate more efficiently with each other. To test this out, to see if we can allow the distribution of language models to shift to different environments, we use this environment from Janner et al. It's a simple 2D grid world environment where you have natural language instructions, such as reach the cell above the westernmost rock, that are attributed to trajectories or paths in the environment that actually follow these natural language instructions. How we formulate this task is we have a speaker agent that is a language model that must learn to instruct a listener agent that is a reinforcement learning model that can understand natural language to cooperatively solve the task. So what the speaker model needs to do is to generate instructions such that when the listener gets those instructions in, this allows the listener to perform, this allows the listener to perform well based on the speaker's instructions. So in order for this to work well, both agents must cooperate with each other. So the listener can only work well if the speaker generates instructions that were good enough for the listener to perform its task, and the speaker only gets rewarded if the instruction that it gave to the listener was a good instruction and allowed the listener to actually reach the goal based on the instruction that it followed. So what this actually means in terms of the actual modeling and the optimization problem is that what the listener needs to do is to estimate its action policy, which is just a standard reinforcement learning policy, by taking in a full natural language instruction and trying to reach the goal. So emit a set of actions in order to execute what the instruction wanted it to do. And what the speaker needs to do is to estimate its generative model, so the language model policy, but now it gets rewarded based on whether or not the listener actually solved the task that the speaker asked it to do. So both agents need to cooperate, which is why this is a purely cooperative task. So one of the questions that we wanted to look at is how do we ensure that when a language model that starts with some amount of natural language information, and when it does this sort of reinforcement learning self-play, a lot of the problems that we had before from the settings where agents just don't start with natural language is that a lot of the language is uninterpretable because it's purely fit to the task, and humans now can't understand it because it started from something that was not rooted in natural language. However, another problem is that this language drift problem can still occur. So even if you start with a vocabulary of natural language, if you max out the reinforcement learning fine-tuning, the semantics of natural language can now drift to something that's purely task-specific and now not really rooted in natural language. So the language learned can get distorted during self-play. How we fix this is, and this is not very different from a lot of the RLHF work that's being done now, although this work was slightly prior to that, but we can combine this sort of self-play reinforcement learning with supervised learning in the speaker's loss function. So you first learn the weights of the speaker model with a small amount of data, and then you optimize with the cooperative self-play reward, making sure that the policy that is being learned doesn't drift too far from the initial policy. We see that if you do this, so if you learn how to interleave between the supervised learning and the reinforcement learning fine-tuning and making sure that the policy doesn't drift too much, you can actually allow two agents in this joint optimization problem now to correctly learn how to cooperate in a task, but also allow the language model to now drift to saying task-specific instructions as opposed to just general natural language sentences. The other thing that we look at is what the minimal amount of data we can use in the supervised phase that still allows prevention of language drift during self-play is. And we see that if you experiment with retraining the speaker with different amounts of held out data, so if you only give it a small amount of in-domain data to learn how to talk about the task in the beginning, we see that with just about 800 instructions of this interleaving of supervised learning and the reinforcement learning fine-tuning is enough to achieve a good enough listener task performance. So both the speaker now learns how to generate in-domain instructions, but the listener also can always accurately take those instructions in and learn how to reach the goal. And importantly also now, the language that these two agents have learned in this joint optimization task is natural language, so it's also interpretable to humans, which is nice to see. In additional work, we also extended this to multilingual instruction following. And again, the nice thing about this cooperative multi-agent setup is that it doesn't really matter what the language that you start with is rooted in, but as long as it's a language that is human interpretable and you have some amount of pre-training that gives you some amount of semantics over a vocabulary to start with. So for example, if you now move to these sets of environments and instructions that are in Hindi or Telugu, or other data sets that contain samples of natural language that are associated with environments, you can perform the exact same settings. So this multi-agent cooperative setting can allow you to now shift the distribution of what your language model knew before to now be purely task-specific and can allow you to instruct agents in this environment efficiently and also in a way that is now interpretable to humans. So in summary, from this talk, we've seen a little bit about how language can be helpful to help multi-agent reinforcement learning environments work a little better. And now what I'm going to talk about is, apart from just using language to help multi-agent reinforcement learning systems, we can actually also use techniques from game theory to now just train the language models better in the first place. So what I'm going to talk about a little bit here is how to do better vocabulary selection to just train any language model better in order to perform a language modeling task. So let's consider a very standard language task. So consider a sentence such as, the food was pretty good, but I won't bother coming back. And you want to classify the sentiment as positive or negative. This is what a standard setup looks like. You have some sort of vocabulary over all of English that you want to have embeddings for your language model for. You then encode all of these embeddings over all of the samples in your training data set, pass it through many attention layers and residual streams until you finally classify the final output of your model. For large amounts of data and large vocabularies, you usually have a huge amount of words, for example, in the English language. And sometimes encoding all of these words is slightly computationally intractable. There's now new techniques about like subword embeddings and other things that you can do. But it's also sometimes the case that you just use heuristics such as frequency of words or information theoretic measures like TF-IDF to cut off the vocabulary, where words that are very low frequency might not be used very often in a lot of the data sets and tasks that you need, which is why you might just exclude them from your vocabulary and just not have them in the task. It's also worth noting that nearly any single language modeling task that we need requires some sort of fixed input vocabulary. So these heuristics are often used to just make the vocabulary slightly smaller, to make the embedding layer slightly more intractable and of a lower dimension. And what we want to look at over here is, can we do a slightly better vocabulary selection instead of just using frequency or TF-IDF, but can we use game theoretic power indices to rank words better, not just based on frequency, but maybe based on how important those words were for this specific task. And this is how we set up these language tasks game theoretically. So the game over here in the setting is actually just the classification task. So for example, sentiment analysis. The players in the setting are the words in the vocabulary, for example, in all of English. And coalitions over here are sets of words that might exist in some sample in your training data set. The contribution, which is the importance of a word that we want to measure, is the gain in task performance. So what we want to see is how important a word was in order to let the language model perform well on that task. And the valuation function, so how we measure this contribution, is by looking at model accuracy on a task. And then finally, the Shapley value is the average contribution of a word across lots of these coalitions for lots of samples in the data set. And what we want to be able to see is whether or not we can find a way of looking at which words contribute the most to the model playing a task really well in order to get this ranking in which we can then exclude some words that were not important to a task at all. So this is a summary of what the algorithm looks like. So for your input NLP data set for a certain task, you have some full vocabulary and a classifier model that can perform the task based on that input vocabulary and the embeddings that they encode the words over. For each word in our vocabulary, we first initialize the Shapley value to 0. And then for every word, for some number of sampled permutations, what we want to look at is when we train the model on a vocabulary of the entire vocabulary minus that word versus the entire vocabulary including that word, was there a significant difference in the performance of the model when it has trained for that entire task? And that difference is the valuation or how important that model was to perform that task. At the end of this, when we do this for many, many samples and also many training runs of the model, we now have these valuations for every single word in the vocabulary. We can rank all of the words in the vocabulary and then cut them off based on how many words we want to keep in our vocabulary. And then what we want to see is whether or not this way of measuring the value of words is better than just looking at the most frequent words or looking at measures like TF-IDF. It's worth noting also that this is massively expensive to do. So what you need to do is to just parallelize this entire, for every valuation that you need, you're running an entire model on a certain task, and you need to perform all of these computations separately and then average them over. What we do for this is we just use like really simple valuation functions. So there's logistic regression classifiers instead of just giant transformers that were trained for the task. And then the end model that we use based on the vocabulary is a giant transformer. We also write the model in JAX for faster computation. And this is actually possible if you do a lot of these parallelization and efficiency measures, and then your final model can be a giant language model that then takes in the input vocabulary. And then given this, I'm just going to briefly go over the results, but given that we have this new ranking with the Shapley ranking of words as opposed to frequency or other heuristics, how much better does this actually do? Like, what is the difference in performance that we want to see? We look at 3 different tasks: document classification, single sentence classification, and also question answer classification. We see, so this is just an analysis for pretty low vocabularies, but you can see that the accuracy of the Shapley ranking versus just TF, which is term frequency, or TF-IDF, is consistently higher than both of those, which is good to see. When you actually look at this on the full vocabulary ranking, there's still always an improvement when using the Shapley ranking as opposed to just frequency and TF-IDF on a lot of just like very standard benchmark NLP tasks that we measure over both document classification and question answer classification. And then we also measure different power indices as opposed to Shapley. One last little analysis that we do is when you, for a given input sample in your training data set, so for example, if you wanted to measure the sentiment of a sentence, if you look at the rankings produced by the different ways of ranking the vocabulary of a word, you can see that the heuristics, so TF, which is just term frequency, and TF-IDF, which is frequency weighted by some sort of document frequency, you can see that frequency just really weights the most common words the highest. But if you look at the Shapley and Banzhaf, which is the 2 power indices, there's actually just like an intuitive difference. Like the words there seem more relevant to the task based on this game theoretic measure of actually looking at how much power that word had for a certain task, which is nice to see. So in summary, I think this was, a very nice glimpse into how there's been a lot of work in multi-agent reinforcement learning and just using language to allow agents to communicate with each other and using reinforcement learning techniques to fine-tune language models. But I think this is a nice way to show that game theoretic measures can also just improve language model training and allow language models to have better heuristics baked into them that might then allow them to train better in lots of interesting ways. And with that, I'm going to end and take any questions.
I'll start with like an open one. I'm really curious. So the idea with like the Banzhaf vocabulary selection obviously just like helps improve the training of large language models. And I'm wondering, like, what do you think are like the next directions for like game theory to be playing, for game theory to be applied to improve like language models, large language models?
Yeah, I think that's a really important question. I think so at this time. So this was not that long ago. I think like the pre-training of language models was still a thing that existed back then. But I think now that like fine-tuning has become such a big thing that does show big improvements in allowing language models to have better capabilities, there's lots of interesting things that you could do over there with using the power indices, such as figuring out like what samples in the fine-tuning stage are actually the most important to allow the model to learn a task better. A lot of the work here we did was not that. This was like at the pre-training level, because it was a few years ago and there wasn't that much work being done on the reinforcement learning fine-tuning. But I think now we're at the point where we have these really big language models that can perform really well. We need to figure out the best ways to like fine-tune them better, either with reinforcement learning or supervised learning. And I think just like deeply thinking about the ways in which we curate the fine-tuning process is super important, but then also I think nicely is one of the ways in which like the game theoretic setting helps a lot, because you can just like properly set, if you can set your task up as a game, you can then determine like what would lead to like the best payoffs, what the best strategy is, and I think that might be a fascinating way to try to use these techniques there.
I think going back to the first part with like the communication, like I feel like there's this, I'm not an NLP person, like there's this trade-off between having like generalist models versus like specialist models, and like have you thought about like making more specialist models essentially communicate with one another, essentially like building protocols amongst them so as to build better models, kind of I guess like a mixture of experts type of thing, but like for large language models, like what are these directions, any ideas?
Yeah, that's interesting. I think historically a lot of the work in training populations of agents together has been not using natural language, so it's often the case that you just start with like some sort of communication policy and then allow the multi-agent reinforcement learning training to just assign some sort of meaning, and you can see that that does allow agents to improve performance a lot better. I think now that we have techniques, or we know that we can start by rooting in some sort of semantics, there's lots of areas to explore there. I think Jacob hinted at like some of the work that he's doing on like guiding language model generations better with like search techniques or like assigning semantics correctly to them. And I think that's a big open area of work that could be exciting.
One more question, because I asked all the
Yes.
questions.
Yes,
I'll answer quick.
Quantitative question, and I think you had the question on one of the slides as well, in terms of how much Shapley values help, how many samples would you need, and how large coalitions would you actually look into? So,
Yeah.
Right. So I was wondering what those results were.
Yeah. So I think for a lot of, so we just used like very standard NLP tests, like just like sentiment classification and question answering data sets that are usually of the order of like 1,000 to 10,000 samples, and we found that with just that much data, with that much data, the vocabularies are usually on the order of like more than 10,000 words. If you perform the computations really quickly, it is tractable enough to be able to just use that. Like that's still like, I don't know, like 10 to the 6, like, or like an order of magnitude higher than that number of computations that you need to perform. But it is tractable to do that. And we have full details of like the things that we had to do in order to make that work. But I think the point that we were trying to make is that we want to work at the level of real natural language processing tasks, which is a lot of data set samples and a lot of words in a vocabulary. And the thing that we needed to do was to figure out how to make the computations work at that level.
Awesome. Thank you, Roma. Our next speaker